Welcome everyone to the last part of MST. In the past three videos, we talked about definition of minimum spanning tree. Then we learned about the algorithm by Borufka, Kruskal, and Janik-Prim. In this video, we'll compare these three algorithms, learn about the history of the problem, and also we'll go over several extensions and examples of MST as well as greedy algorithms. We'll talk about general framework of greedy algorithm and and the references for greedy algorithms. Now, the reason I chose minimum spanning tree to start greedy algorithms is because it's the prototypical problem for greedy algorithms. And there are several ways you can obtain greedy algorithms which will work perfectly for minimum spanning tree. And for that reason, I'm talking about the history where we see tens of people arrived at the same algorithm or similar algorithms at different times. So the oldest algorithm in the beginning, we talked about the story of Swadesh and Mohan Bhargava and Otakar Borufka. The Otakar Barufka, his friend Genrich Saxel gave him a problem to construct the electrical network connecting several cities in East Moravia using least amount of wear, which was the electrical problem. And he published this first paper in 1926. And after that, it was rediscovered by Gustav Choquet in 1938, a team of Polish mathematicians led by Joseph Lucas Jewicz in 1951. Sorry, the pronunciation is wrong, and George Solin in 1961. And that's why many textbooks on distributed algorithms, they mention this to be Solin's algorithm as well. For Prim's algorithm or Jernik-Prim's algorithm, Jernik was the first person to discover the problem, the algorithm, and in 1929 he wrote a letter to Borufka and published his discovery in the next year. The algorithm was independently discovered by Kruskal. This is not the Kruskal's algorithm. We are talking about Prim's algorithm or Jernik-Prim's algorithm, but Kruskal also independently discovered this in um, in the same paper where he wrote his famous Kruskal's algorithm. Also by Robert Prim in 1957, Harry Loberman, Arnold Weinberger, and finally Dijkstra in 1958. The same Dijkstra, if you think, Dijkstra's algorithm is very similar to Prim's algorithm, so it's no surprise that he also came up with the same algorithm. For Kruskal's algorithm 1956, Kruskal thought that he was motivated by a typewritten translation of obscure origin of Borufka's original paper that had been floating around the Princeton math department. He found the algorithm to be unnecessarily elaborate, and then same algorithm was rediscovered by the same people who also discovered Jernik's algorithm, Harry Loberman and Arnold Weinberger. So just to avoid long names, we just call Jarnik Prim, Kruskal's and Borofka's algorithm as the name of the algorithm. Now, many textbooks don't teach Borofka's algorithm. When you're teaching in the class, many of you told me you know about Jarnik Prim's algorithm or Kruskal's algorithm, but Borofka is not so popular. But it has several advantages. So this is a code by Jeffrey Richter. This is the MST algorithm you want, Borofka's algorithm. The reason being, we saw that Borofka, that there's a loop which connects the components and that transfer log v number of rounds, because initially you start with v components and then finally each round it halves. But in practice, normally it can be much faster. Even all the things can be connected by a constant number of iterations. Not you don't need log v number of iterations. So the number of components can drop significantly. And in those cases, Borofka can perform very good. Second, Borofka's algorithm can work very well for several special cases like planar graphs. There actually you can get a order E time algorithm for the problem. Then Borufka can also allow significant parallelism. Each of the component can be handled separately parallelly. And the fourth part, which is more important, is this is actually building block for many other algorithms, which broke the barrier of all these three algorithms. So all these three algorithms, in the worst case, they will take something like E plus V log V or E log V time. So there is a V log V or E log V barrier, which we call sorting barrier. We have to sort the edges or vertices, some kind of runtime like V log V is coming. Can you break that? And there are algorithms which have broken this sorting barrier, and all of them are based on Borufka's algorithm. So this was the present known best algorithm by Bernard Schagel. The runtime is order E times alpha E, where again alpha is this Ackermann function. So it's almost linear, but not really linear, because alpha, as we talked earlier, for practical purposes, alpha E is less than equal to 4 or 5, but it's still a slow growing function, so it's not really linear. But we have another paper by Seth Petty and Vijay Ramachandran, which appeared in JSCM 2002. where they gave another algorithm and showed this is the optimal algorithm. It really does optimal number of comparisons, but it does not explicitly mention the value. So we know the lower bound you have to do at least order E, and the upper bound is from Chazer's algorithm. Already we know it's order E times alpha E, so somewhere in between. So it might be possible that the problem actually admits a linear time algorithm, order E time algorithm, but and this is the algorithm which is order E time, but we don't have the analysis to say that. But on the other hand, both these algorithms are deterministic algorithm. Randomized algorithm, which is a very powerful tool, we'll learn about randomized algorithm in the later part of the course. That actually gives a very simple algorithm, which is by Kargar, Klein, and Tarjan, and they gave this in JCM 95, which was even before Chazel's paper. That can give you a order E time in expectation. So there's a randomness here, some kind of random coin tosses will be there, and based on that you take some decisions. But in expectation, it will run in linear time, in order E time. Now, quickly let us compare these three algorithms, Kruskal, Prim, or Barufka. So Kruskal, as we saw, it's a simple and intuitive algorithm, so very simple to implement. This is probably the first algorithm people learn. We also learned this is the first algorithm in this lecture series. And it works very well when the graph is sparse. So we have this E log E time. So if the graph is sparse, let's say planar graph, E is roughly order V. And then it is quite fast. It works well with the edge list representation. And also you can use parallel algorithms for the algorithm. The issue with this is if there are too many edges, the graph is dense, then it is E log E, which can be quite bad. It could be in that case order V square. So it could be V square log V. And you need data structures like union find, complicated implementation. That can be problematic. For Jernic Prim, the runtime is order E plus V log V if you use Fibonacci heap, and it works well with adjacency matrix representation. It's very good if the graph is dense, and it's good if you want to construct the MST incrementally from a source. The problem is if the graph is sparse, then it is not as elegant as Kruskal. You also need this complicated Fibonacci heap or some other kind of priority queue for implementation. And you need the graph to be connected. Otherwise, you have to go for different component if you run it separately. So yeah, so that's the best case is dense graph case, use Yannick Prim's sparse graph case, use Kruskal. Borufka, we already mentioned for many graphs like planar graphs, it's much faster. It's good for distributed and parallel computing. It's simple and elegant. It's parallelizable, and every time the components actually, it might be shrinking much faster than the worst case. But of course, you have to keep some bookkeeping of components and edges. There are pros and cons. So all these three algorithms are good to know. But if you want to implement, maybe Borufka is a nice algorithm to implement, and the variants of Borufka in general. Now let me talk a little bit about different variants. So we talked about spanning tree problem where the graph is undirected and weighted. Now think of the directed graphs. And I asked a similar question. I have a directed graph and I have some root vertex. And I want to find a subset of edges such that all vertices can be reached from, from this root vertex. So that's called minimum cost. And I want to minimize the cost. That's called minimum cost arborescence problem. And surprisingly, even a greedy algorithm for this works, which is more complicated. In Klein-Bartolus algorithm is mentioned. But then the interesting thing about MST is if I slightly add more constraints, many times it becomes suddenly NP hard. So think of this question that I want to find a spanning tree, but I require that the degree of each node should not be too large. A spanning tree can be a star where there is a central center vertex and there are n minus one edges connected directly with n minus one vertices. But let's say I don't want that because then this vertex becomes very it has too much load. But I want every vertex should have degree at most 2. So then it looks like a path. But the spanning path problem is called Hamiltonian path problem, which is or traveling salesman problem when you have cost, which is already NP hard. Or there is other question called survivable network design problem. Here in our problem, we start with an empty graph and then we build and we get a tree. But maybe in some other problems, some edges are already present. That's already there. Some road networks are already there. And then we want to build some more roads on top of this network such that the graph is connected, even better connected. So, for example, if I have a tree, it's not that great for connectivity. If one edge, there is a fault in one edge, then the graph becomes disconnected. But maybe I want k edge connectivity. So, even if there are k minus 1 edge faults, the graph still should remain connected. So, those are called survivable network design problem where the graph should be connected under some edge fault or vertex fault. And then other question is called minimum spanning standard tree. In the problem of spanning tree, we are only using the nodes which are given to us. But in standard tree, we can also add some other nodes which are not part of our graph, and it can reduce the cost. Think of this example that I have 3 nodes here, and if I add and there is a Euclidean distance, whatever the distance in the plane, if we add them, then we probably have cost like this triangle. But if I add a Steiner node in middle and then add edges like this, we'll see the edge cost is smaller. So in that way, think of this in Swadesh movie, if I create one additional electric post, not in the houses, but somewhere intermediate space, it can reduce the connectivity cost further. That's called Steiner tree. But that's a much harder problem, and that's actually NP complete. So there are several variants mentioned in Wikipedia page. I just mentioned Steiner tree, then Euclidean variant, K-linear spanning tree, rectilinear spanning tree, distributed variant, degree constant variant, arborescence, and so on. So if you want to know about the details, check these variants. For applications, as it's a very fundamental question, it appears in many, many places, including computer networks, telecommunication networks, and cluster analysis, image restoration, segmentation, etc. This spanning tree algorithms are also a building block for many other problems. For example, traveling salesman problem that I mentioned, it's one of the key problems in commutative optimization and approximation algorithms. And there, the most famous fundamental algorithm was Christophil's algorithm. And it's also a variant for Steiner tree as well. Both these algorithms use spanning tree algorithms as a subroutine. So for a lot of theoretical algorithms, spanning tree algorithms are also used as a building blocks. So that for that reason also, it's very important to study. I will not mention the details about the problems in competitive programming, but if you go to the CP algorithms page, you will open this and you will find many, many application problems, interesting programming questions. Please go over them. I'll probably also post some homework questions or practice problems. There are several interesting practice problems in spanning tree, and the only way to learn algorithms is by solving problems, by writing pseudocode or even implementation. So for example, in Jeff Erickson's book, it's free. A lot of exercise problems are there, or Corman, or other textbooks. I'll mention some problem, but you can open any textbook and you try to solve. It's okay if you're not able to solve all problems, but just going over the exercise to think about a problem and understanding the problem structure in more detail will help in the long run. Finally, this is also a very nice, important problem for my research. For example, I worked on network design problems where this is one of my publication on matching augmentation problem where we start with some graph, in this case it's matching, and then I want the graph at the end to be two edge connected spanning subgraph. So it's instead of tree, it's a more generalization. In this graph, even if one edge is deleted, the graph should be still connected. So it's two edge connected graph and then it's spanning subgraph. So in case of tree, it was one edge connected spanning subgraph. This is two edge connected spanning subgraph, and there are a lot of follow-up works after this work. So this is a very active area of research in approximation algorithms. Let me conclude with greedy algorithm. So we saw one example of greedy algorithms. A greedy algorithm is an algorithm that builds up solution in small step in each time where we're choosing something very myopically. So advantage of this is very easy to implement and quite fast. But the difficulty is it's very difficult to find the right metric. And for most problem, we don't have enough sufficient structural property for greedy to use. We'll see later, dynamic programming is much more useful compared to greedy. So this is the message from this movie called Tumbar. If you have seen, you know the famous dialogue, Lalchi hai tu, and then greed was the reason of the failure. So greed rarely works. It's good to understand to start with, but for most problems, you need more structures to apply greedy. So dynamic programming or linear programming or other techniques are more helpful. But we'll still learn some greedy because it's very elementary way of thinking in algorithms. It's okay to get some intuition in the beginning. So there are two ways to prove why greedy works. One is greedy stays ahead. For example, in this case, we were kind of showing that each step, whatever greedy is doing, is same as the optimal algorithm. The second will be exchange argument. We'll see later when you talk about fractional knapsack or interval scheduling problem. We'll use some kind of exchange argument to prove that if greedy is not optimal, I can take any other possible solution to the problem and gradually transform it to the greedy solution without hurting its quality. So if we take optimal solution, we can get another optimal solution, which is a greedy solution. And that's called exchange argument by exchanging a little bit. So we'll see some examples later. Now let me talk about the references. So I primarily followed Jeff Erickson for this chapter, chapter 7 for MST, but there is Klein-Bachtados or Dasgupta, Papadumitra Vezirani, CLRS, Team Robin, all books have MST. It's a fundamental question. Data structure I did not cover much. If you want to know about heaps, chapter 6 in CLRS or chapter 21 can be for disjoint set data structures. And then I'll cover interval scheduling. Later, this references I'll follow and fractional knapsack. There are several other questions like Huffman code. This is mentioned, or some scheduling question like optimal caching, scheduling to minimum lateness problem. There are more complicated exchange arguments which are mentioned. Shortest path problems, clustering problems, and arborescence problem that I mentioned earlier, directed graph variant of MST. There is a multi-phase greedy algorithm in Klein-Bachtados. You can go over them. Then there is Horn formula and set cover, which is an NP-hard problem. But even for NP-hard problem, there are greedy algorithms. Sometimes they give very nice approximation algorithms. Furthermore, there is an object called metroids, and greedy algorithms work very well for metroids. For example, Kruskal's algorithm can be seen as an algorithm on graphic metroid. Or task scheduling is another problem which can be seen as a metroid problem. So if you're interested about metroid, you should read about CLRS, why these things can be formulated as object metroid and can be solved. Metroid are very powerful objects in combinatorial optimization. If I get time, I'll probably add some videos on metroids. This is an advanced topic. So if you're interested in theoretical CS further, then I highly recommend reading about these things. So this ends our lecture on MST. Hope you have learned about MST and greedy algorithms. And the next lecture, we'll talk about dynamic programming. Thank you.